All right, friends, based on a couple questions after the last hour, I just wanted to take another shot at explaining something. Felt like I did sort of a poor job of this. This example was meant to illustrate, this example was not meant to show you how to calculate something. This example was meant to illustrate how, if your reaction involves charged groups, the bond dissociation enthalpies don't give you the whole story. The reason for that is that bond dissociation enthalpies don't deal with charged reactions at all. Remember, they deal with the situation where you break the bond and each partner gets an electron, not the situation where you break a bond and one partner gets the electrons and the other partner gets a positive charge. And so bond dissociation enthalpies are not going to account for differences in stability of charges on one side of the equation versus the other. So notice in this reaction, despite what I said, we are breaking the carbon-hydrogen bond, the carbon-bromine bond. We are making a carbon-carbon pi bond and an OH bond, but, and these numbers account for those changes, but what they don't account for is the difference in stability of the alkoxide versus the bromide. And the pKa stuff was just, remember how we use pKas? We justified pKas by the stability of the conjugate bases. Br minus is a very stable conjugate base of a very strong acid, whereas the alkoxide is a reactive conjugate base of a very weak acid. So all I meant to say is be careful using bond dissociation enthalpies to decide whether a reaction goes in the forward or reverse direction. It works best when there aren't any charges involved. If there are charges involved, you need to think about differences in stability of the charged molecules. I would not have asked you, nor will I ask at this stage, for you to predict whether this reaction was forward, favorable in the forward direction, or reverse, in part because it would be complicated to figure out how to offset this number from bond dissociation enthalpies with the dramatic change in stability of conjugate bases. To get the idea, if charges are involved, be careful. That's, the BDEs don't give you the whole picture. Any follow-up questions you want to ask about that? Yeah.
So we got that question on the test, hypothetically, which you probably won't. We just look at the bromine, right? It's way more stable, and you would say, okay, it favors products because it's more stable, must dissociate, therefore products.
Yeah, retrospectively, knowing that it's favorable, then yes, that's a decent explanation. If I put this on the exam, what would happen is you would answer what you thought was best, and then depending on whether I counted it wrong or not, you would come to my office and explain to me that I did something wrong, and then I would give you the points back. Is how it works. Okay, so I won't give you something like this. If I were to give you a reaction, it would be more like the one we did previously where things were neutral. Okay, other questions? Oh, and by the way, since the test is multiple choice, I can make such changes uniformly for everyone in the class by changing the key so that everybody gets the points back instead of just those intrepid souls that march to my office, right? Yeah. Yay, all right. Points for everybody. So, kinetics. Kinetics is an issue of how reactions happen. So I'm going to show you a reaction that we'll get to in the next few lectures. And we're going to discuss various possibilities for how the reaction occurs. This is an issue of mechanism. Okay, so this reaction involves a charged cyanide ion and neutral methyl iodide. It's a substitution reaction because we're going to swap out the cyanide for the iodide. Our product is going to be this product, and we'll get I minus as a byproduct. Okay, so a couple of sort of things to be aware of. In general, you might have called these reactants. that's fine, but I tend to use the term starting materials. So if I say starting materials, that's what I'm referring to. I will often, in a hurry, abbreviate that as SM. These are products, which I might abbreviate as P. You can tell this is a substitution reaction because carbon used to be bonded to iodide, and now it's bonded to cyanide. Okay, so the issue of kinetics actually doesn't really address the issue of whether a reaction is favorable in the downhill direction or not. I will tell you that this reaction has an equilibrium constant greater than 1, meaning the delta G is less than 0 and it's favorable. Part of that is the fact that I replace a weaker carbon iodide bond with a stronger carbon-carbon bond. And the other part is that I replace a more reactive negatively charged thing with a less reactive negatively charged thing. And you could tell that I minus was less reactive because its conjugate acid has a pKa of like minus 11, whereas HCN has a pKa of 9. So again, 20 orders of magnitude to trade one for the other on top of the change in bond energy. So this is a favorable reaction. It works really well. But whether or not it's favorable doesn't necessarily tell you anything about what the mechanism is. Okay? So before we figure out how the reaction happens, it's good to summarize what happens. So the what here is that we have to break the carbon iodide sigma bond, and we have to make a carbon-carbon sigma bond. And that's it, okay? Just two things to worry about. So that's the what. Now let's deal with how. And let's think of some mechanistic hypotheses. And in doing this, you're going to be doing what chemists do when they discover a new reaction. That is, they come up with potential mechanisms, and then they design experiments and or do calculations to determine which of those mechanisms are unrealistic and which are more likely candidates. So option 1 could be that we make the carbon-carbon bond first, and then afterward we break the carbon iodide bond. So what would this look like? Let's see, option 2 could be that we break the carbon iodide sigma bond first. We get some intermediate, and then afterward we make the new carbon iodide sigma bond. Oops, sorry, carbon cyanide sigma bond. And then option 3 would be that we make the new carbon cyanide sigma bond at the same time as we break the carbon iodide bond. That makes sense? There's sort of 3 different extremes of mechanism that we can imagine. So now let's sort of think about how this process would occur and what the intermediates would look like. So I'm not gonna redraw the starting materials in these mechanisms. I'm just gonna say starting material. If we made the carbon cyanide bond first, you might expect to get something like this as an intermediate. You'd have a new bond between carbon and cyanide. At the same time, you'd have a new bond, you'd have the old bond between carbon and iodide, and then you'd have 3 other things, the carbon-hydrogen bonds attached to the carbon with a negative formal charge on the carbon. Does that and then presumably after that, you would break the carbon iodide bond such that iodide left, and you then had your new product, which I guess, well, now that I've drawn them, I just as well draw them. Keep drawing, sorry. I press record, good. Okay. This intermediate maybe is giving you some heartburn. Why? We got 10 electrons around a second row element. That's a no-no. And also we have a related issue is we have 5 bonds to carbon, which is also problematic. Okay. On the other hand, that's only because we know the rules, and if we didn't know any of the rules, we could certainly propose that and see and design some experiments to test whether that was the case. When imagining a mechanism, it's good to think about the transition state. And sometimes it's helpful, I guess I'll just go ahead and draw the starting material. Sometimes it's helpful when you're thinking about the mechanism to draw arrows. And most of the time in organic chemistry, when people are asking you to draw a mechanism for the reaction, they want to see arrows. And the arrows tell you what bonds change during a step. So in this mechanistic hypothesis, we first make the carbon cyanide bond. We would indicate that with an arrow from the lone pair electrons on cyanide to the carbon and nothing else, and then that would be the new bond that we formed. And then in going from this intermediate to products, we would show the iodide carbon bond breaking. So this would be step A, and this would be step B. All right? And then you can think about transition states, which are, you sort of estimate what would it look like when this reaction is at its maximum in energy. For most reactions, there's an energy barrier before where you go up in energy. You have to surmount a hill. It's called activation energy before the reaction happens. In this case, the hill that you're going up is related to the repulsion between the electrons on this nucleophile and the electrons in the carbon-hydrogen bonds. You got to overcome some of that. Yeah.
I'm just curious. So whenever the CN attaches to the carbon, that creates energy, right?
If you make a new bond, you would predict.
So if it creates energy, could that energy then be used to break the iodine bond? Or
So your question is a good one, and yes, making a bond can pay for breaking a bond. Yes. In this case, this mechanism, I will just tell you, is not reasonable and it's not consistent with the data. But
This takes way too much energy for the NC. And then also
because we're going to see. I mean, a spoiler alert. Here we've proposed that this is an intermediate, but it turns out this is a maximum in energy. So this is actually a transition state. If you were to do the calculations, you would observe that this is the energy high point. So that means it's not an intermediate. You don't pause at this state. That's the maximum in energy. But, I mean, if you had to envision what a transition state would look like for this reaction, presumably it would involve partial formation of a bond between carbon and cyanide. At the same time, maybe the rest of the bonds are rearranging to be closer to what we've got here. In transition state drawings, we use dotted lines to indicate bonds that are forming versus breaking. We use delta minuses, little Greek delta minuses, partial positive or negative charges to indicate that we used to have a negative charge on cyanide, but as we form the new bond, that charge is decreasing. So we'd call this a transition state, or TS. That's an energy maximum. If we were proposing this as an intermediate, we would say, okay, so that would be an energy minimum near this maximum, and then presumably there'd be another transition state where we had fully formed the carbon iodide bond at the same time as iodide is leaving. This would be the second transition state. And we could propose an energy diagram for that mechanism. We might say, okay, well, you start out at starting materials, you go through some high energy transition state A, you get an intermediate I, and then you go through transition state B to get to products. The important point is not the relative energies of transition state A or B. The important point is also not the relative energies between starting materials and products. The point is that in this mechanism, we've proposed two steps. So we got to go through an energy maximum to get to the intermediate, and then another energy maximum to get to the product. That's sort of what we would expect it to look like. This is a reaction coordinate energy diagram where this axis represents energy and this axis represents reaction progress. And you can measure that in any number of ways. We're just going to be generic about it. Okay, so that's one hypothesis. Okay. Let's look at the second possibility, breaking the carbon iodide bond first. What would that look like? So presumably this would involve the carbon iodide bond breaking to give you a carbocationic intermediate. And so this would be I minus is your sort of leaving group. We form this intermediate I, and then Cn minus would make the new carbon cyanide bond. This would be step A, this would be step B. Here's your new Cn minus bond. You could draw the transition states. Presumably the first one would look like the iodide had started to leave and we were building up partial negative on the iodide and partial positive on the carbon to get to this carbocationic intermediate. And then going from iodide, or going from the carbocation Cn minus, presumably the transition state would look like we're starting to form a new carbon bond with a delta minus on Cn minus as the bond, on Cn as the bond forms, and a delta plus on carbon that's also going away as the bond forms. All right. If we were going to draw an energy diagram for this process and sort of predict what happens, what do you think this step between starting materials and products, do you think that's uphill or downhill in energy? Probably uphill, not sure by how much, but breaking bonds is always uphill, right? So you would predict that you'd have starting material here, uphill in energy to the intermediate. And then what about this step going from intermediate to product? Should be downhill. Okay, so products is down here. Good. What do you think about transition state A versus transition state B? Which do you think is higher in energy? Probably A, because you're breaking a bond there, whereas here you're starting to form a bond. In any case, even if they're very close in energy, the activation energy for this reaction is EA. That is the difference in energy between transition state and starting material. So that's activation energy. And so you can see that the activation energy for the first step is much larger than the activation energy for the second step, right? To get from starting material to intermediate, you have to go all the way up here. To get from intermediate to product, you're already up here. It's much easier to get down to the product. Because of this, we would predict that our first step would be the rate determining step, or RDS. That's the slowest step that we have, and it's going to be the one that's most uphill. Yeah?
So for the activation energy of the second transition, or like if the products from the intermediate would be TS minus I.
Yeah, for the first step,
It's TS.
it's transition state A minus starting material. For the second step, it would be transition state energy minus the energy of I. All right. Have you heard of the term rate determining step before?
Yeah.
Okay. All right. Otherwise, I was going to start talking about a sandwich assembly line analogy from my distant past, but I think we'll just forego that. I was the rate determining. No, actually, it was Adam. He was 5 at the time, and he was the rate determining step. It did not matter how fast Amber was bagging up the sandwiches and putting them in brown paper bags. She could do it no faster than Adam was making the sandwiches because he was the slow step. Now, in a lot of other processes in life, I am the slow step. But yeah, go ahead.
Is it important to know why the transition states are higher in energy than the intermediate?
Is it important to know why the transition states are higher in energy than the intermediate? Probably not, as long as you remember that they are. But if you want a real answer, think of it this way. In the transition state, you've lost some of the stability, much if not most of the stability associated with this carbon iodide bond. And now think of the most stable arrangement of the remaining carbon-hydrogen bonds afterwards. Did you notice that I drew this carbon as though it were sp2 hybridized? And that's because of valence shell electron pair repulsion. We want to get those carbon-hydrogen bonds as far apart as possible to minimize repulsion. And that has not yet totally been done in the transition state. So you've still got some repulsion that you need to relieve by flattening out. And that's why it's higher in energy than the intermediate. Though you'd predict them to be pretty close in energy. And they are in fact close in energy, and you'd predict them to sort of resemble each other. Similarly here, in this transition state, you're fighting against the repulsion of these carbon-hydrogen bonds with each other, but trying to pay for it with the strength of the new bond that you form. And presumably at this stage, it's not totally offset yet. All right, that kind of thing, changing shape, is called reorganization energy, and it's usually unfavorable. Okay, anything else we need to add about that? So, what do you think about mechanism 2 in terms of reasonability versus mechanism 1? Seems more reasonable in the sense that we're not breaking the octet rule. Okay? Right. So let's try mechanism 3. We're going to make the carbon cyanide bond at the same time as the carbon iodide bond is breaking. So here's Cn minus. I'm going to show formation of the carbon bond with that arrow. And at the same time, I'm going to show breaking of the carbon iodide bond with this arrow. And that process would take me directly from starting materials. Whoa, I meant to draw an H there. That H was lying down on the job. We go directly from starting materials to products. The transition state for this reaction presumably would look something like this. We would have some intermediate where iodide, or some transition state where iodide was leaving at the same time as Cn minus was coming in. We wouldn't know exactly whether Cn minus was coming in faster than iodide was leaving. Depending on which one left versus came in, we might expect the carbon-hydrogen bonds on that carbon to be leaning in either direction. But this would sort of be the transition state. And then this would be our product. We don't have an intermediate proposed here. This is not an intermediate, it's a transition state. We're saying it's an energy maximum. So our energy diagram would look something like this with this high energy transition state. We would call this reaction concerted because the bonds that you break and the bonds that you form are all happening in the same step. All right, questions you want to ask about option 3, hypothesis 3? Yeah?
Would the transition state energy be higher than what you see in the other ones?
Would it be higher than what you see in the other ones? That is a great question, and the answer is it depends. We're going to see, actually, I mean, spoiler alert, that mechanisms 2 and 3 are possible, and whether you go through the mechanism for 3 or the mechanism for 2 depends on the height of this transition state versus this one. And if it's easier to go over this one, then we'll take this pathway. If it's easier to go over this one, we'll take this pathway. We're going to learn what makes those transition states higher or lower in energy, and then it's going to be easier to make that call. Okay, yeah?
You said the third mechanism is a conserved reaction.
Yes.
The first two are called stepwise.
That's right. So the first two, because they have an intermediate, we would call both of them stepwise reactions. Okay. Notice the difference between intermediates and transition states. Intermediates are also high in energy, but they occupy energy minima instead of maxima. All right. You don't want to know this, but I'm going to tell you anyway. How, in any kind of curve with calculus, how do you identify minima / maxima? Take the first derivative, and if it's equal to 0, you're at either a maximum or a minimum. How do you identify maxima versus minima? Second derivative. And so if you're at a minimum, the second derivative is going to be positive in all possible directions. And now we're talking about, you don't want to know this either, a multi-dimensional energy landscape. Whereas at a maxima, the second derivative is negative in one direction. Anyway, you don't want to know that. It has to, but I don't know why I told you, other than I recently learned it and I'm still geeking out about it. So I apologize for that. Will calculus be on the test? No. All right, so we've got some possibilities. Oh, the other thing I wanted to highlight is notice the subtle difference between mechanism 1 and mechanism 3. The transition state for mechanism 3 looks basically the same as the intermediate for mechanism 1. So the only difference between 1 and 3 is whether we say this is an intermediate or a transition state. That's to get from mechanism 3 to mechanism 1, what we would basically be saying is, oh no, why can't I zoom in anymore? We would basically take our finger on that transition state and push it down so that it was an intermediate. Discerning between mechanisms 3 and 1 is difficult and is going to require calculations. And perhaps also experiments designed to observe intermediates. Intermediates because they occupy energy minimum, they have a longer lifetime, so you can do experiments that observe them. In contrast, transition states have a lifetime that's about as fast as it takes for a bond to vibrate, and so that's small enough that we can't observe transition states. So I will just tell you that computationally, first of all, we haven't observed this kind of intermediate, at least not for this reaction. And computationally, this is a maximum rather than a minimum. And I can show you that if you want to come to my office and see my computational chemistry skills. I can show you some calculations I've done that indicate this is a maximum. So 1 is not reasonable, but 3 is reasonable. 2 is also reasonable in the sense that we're not violating any of the octet rules. And we have observed carbocations as intermediates before. So now we got to decide how would you do an experiment to discern between mechanism 2 and mechanism 3. And this is where the concept of rate determining step comes in. All right. Do you remember writing rate laws for simple reaction mechanisms? Ish. Okay. So the rate law for mechanism 2, I'm going to give us just a little bit more space for mechanism 3. The rate law for mechanism 3, the rate would depend on what? K is a rate constant. That rate constant is related to activation energy. I told you that only the rate determining step matters. It's the one that determines the rate. So when you write a rate law for this reaction, it's got to involve all the molecules that are part of the rate determining step. So yeah, go ahead. So products over reactants is equilibrium constant. Yeah, and that's good. Products divided by starting materials, concentrations, depending on how many you have, it's products, whatever. But yeah, rate law is a little bit different. Rate law involves the concentrations of those molecules that are involved in the rate determining step. So for our proposal mechanism 2, cyanide isn't involved in the rate determining step because the rate determining step is just I minus leaves. So our rate law would sort of look like this. Okay, it would only depend on the molecules that are involved in the rate determining step. Okay, so if we did, now we could do an experiment, right? If we could vary, we would need to be able to measure the rate. Our experiment would be measure the rate as I change the concentration of the methyl iodide. And then I would also measure the rate as I change the concentration of Cn minus. Now tell me, based on this rate law, what I should expect if mechanism 2 is, I don't want to say true because in science we never prove anything that's true. That's a philosophical discussion we should have, but not now. If mechanism 2 is operating, if that's the one that the reaction's going through, what do I expect to see if I plot rate versus concentration of methyl iodide? What does my rate law tell me? Yeah, straight line, linear, right? That's rate is linearly related to, and so I would do the experiment, I would plot the values, and then I would do some linear regression and figure out what the slope was, and the slope would be the rate constant, and that would tell me that this reaction is, and we would use the term first order, this reaction is first order in methyl iodide. Because in the rate law, the concentration for methyl iodide is raised to the power of 1, or in other words, the plot is linear. Now, what should I expect if I change the concentration of Cn minus for this reaction? Told you it's not involved, therefore I could change it and nothing would happen. We would call that zero order in Cn minus. Meaning, okay, you can put Cn minus in the rate equation, but it's raised to the 0 power, so it just ones out. This particular conclusion bothers some students because they look, the product actually has a carbon cyanide bond. So how can you say the concentration of cyanide doesn't matter? Because if it's 0, nothing happens. And the answer is, you're correct, at lower concentrations of cyanide, what's the rate determining step starts to change and the rate law becomes a little more complicated. But in most concentration regimes that you'd be dealing with, you would be comfortable in saying, hey, increasing Cn minus doesn't do anything. Go ahead.
Is this rate law in reference to the first step or the whole thing?
Is this rate law in reference to the first step or the whole thing? And the answer is yes. It is the rate law for the first step, but because that is the rate determining step, then it's the rate law for the whole reaction. Now, if you want to get into it, you can write more complicated rate laws, but what you would observe is that at most concentrations of Cn minus, you can make assumptions that cancel it all out to just this. Yeah. Okay. Other questions? All right, so now we have a prediction. We can go in the lab and do this experiment and see what we observe. Let's think about the same experiment for this concerted reaction. What do you predict the rate law to be? There's going to be some rate constant. The rate determining step is the one that, the only one there is, and it involves both of our starting material. So what should my rate law be? Concentration of Cn minus and concentration of the methyl iodide. By the way, writing a simple rate law for a reaction step just means you use the concentrations of each molecule that's involved in the reaction. If it were 3, we would need 3 terms. If it were 4, we would need 4 terms. One secret is that it's actually really rare / borderline impossible for 3 molecules to find each other directly in solution at the same time. But that's really neither here nor there. What we mean by this rate law is that the key rate determining step is the one where Cn minus finds CH3I. Okay, so if that's our predicted rate law, let's do the same experiment. Let's vary the concentration of CH3 minus while keeping the concentration of Cn minus constant. And then let's do the same with the concentration of Cn minus whilst keeping the concentration of CH3I constant, just like we did above. So we would predict for rate versus methyl iodide concentration, we would predict a linear relationship. Overall, we could fit the data, the slope here would be equal to the rate constant times whatever concentration of Cn minus that we're using. And we could do this reaction, do this experiment at multiple concentrations of Cn minus and get some good information. Otherwise, we could, in parallel, change the concentration of Cn minus, keeping the concentration of I minus constant, and we would get some other linear relationship where the slope here would be equal to K times whatever the concentration of methyl iodide is. And doing so would indicate first that the reaction is first order in methyl iodide and it's first order in Cn minus, and that it's because there are 2 concentration terms in our rate law, the reaction is second order overall. Okay? Any questions you want to ask about that? I know we're going through rate laws a little bit quickly, but that's because I think you sort of know that already. Yeah, go ahead.
I'm just going back to the first option because we just did the second and third. We know through experiments that we aren't doing and information that you just gave us that we're not going to think one is very viable, or by looking at it, can we know that one isn't viable?
So the thing that would tell you that one isn't viable is that you've got a Texas carbon, and you would have to know because I told you that those aren't reasonable. And the real answer is that this is not a low energy point on the landscape, that there are other lower energy points nearby.
Okay, because I know that's Texas carbon, but then in option 3, the intermediate, or not the intermediate, the transition was also
right. And this kind of thing is okay for a transition state.
Okay.
It's because you're not trying to claim that it's a stable molecule. You're just saying that's a high energy maximum that you're going through.
Got it.
So, and it's not technically a full-on Texas carbon because the bonds aren't completely formed. Yeah.
And how would you determine whether 2 or 3 is the better option?
Okay, so how do you determine whether 2 or 3 is the better option? Well, for the reaction, you do the experiment. And if you observe there's 0 order dependence on cyanide, then you say, okay, it's mechanism 2. If you observe first order dependence on cyanide and first order dependence on methyl iodide, then you say, okay, it's probably mechanism 3.
Okay.
So
Yeah,
you want to predict though.
So like on the exam,
So we're not ready on this exam to predict which is the mechanism that's right. I suppose if I gave you data, using what you know now, you could conclude which one is right, right? But predicting which one is right is a little bit more complicated. And we're going to see soon that the rate of mechanism 2 is going to depend a lot on the structure of the starting material and on the carbocation. And so we're going to see that as you make the carbocation more stable, you make this transition state lower in energy, and that can make this reaction faster. We'll talk about how to make that carbocation more stable. It's very simple. We will also talk about what makes another thing that can accelerate this first step. Notice in the first step, I minus is here, it's left with its electrons. So if you make that, we're going to call it a leaving group now instead of a conjugate base because it wasn't used to be, it's not attached to hydrogen in the beginning, it was attached to a carbon. But we'll use our pKa intuition to say, hey, if we make this more stable, a better leaving group, that lowers the energy of the intermediate, it also lowers the energy of the transition state, and it makes that process faster. We're going to see that making the leaving group better also accelerates mechanism 3, but we're going to see that the structure of the alkyl halide and the identity of the nucleophile can promote mechanism 3. If your nucleophile here is higher in energy and more reactive, then it should be, then you start out higher up the curve and then getting over it is faster. But if you're, we're going to see that there are some things about your methyl iodide or your alkyl halide starting material, some structural features that can actually slow down and make this transition state higher in energy. Just a brief preview, nothing to worry about for this exam, is that if you start to add other alkyl groups here to make this carbon more sterically hindered, it starts to get harder and harder for the nucleophile to approach the methyl iodide, and that moves this transition state higher in energy. So presumably at some point, the transition state for mechanism 3 gets high enough in energy that it's easier to go over the pathway through mechanism 2. So we're going to see a spectrum, a trade-off between these two possible mechanisms for substitution reactions, and we're going to learn some rules that help us explain the outcomes of these reactions, but it all goes back to how high in energy the transition states are relative to each other. You're going to see that this substitution reaction that depends on only one thing, we're going to call that unimolecular, meaning there's only one concentration term in the rate law, unimolecular nucleophilic substitution. And we're going to abbreviate that as, and this is a term that will now haunt you until exam 3, SN1. And we're going to call this reaction where there are two concentration terms in the rate law, bimolecular nucleophilic substitution. And that is SN2. Now, just in interest of full disclosure, SN1 reactions are not particularly useful. And SN2 reactions can be useful, but they don't enable us to make a lot of carbon-carbon bonds, which is what we really want when we want to increase the complexity of the kinds of molecules that we can reach. So these are fairly simple reactions, but we're using them as a way to take you through understanding all of the issues associated with reaction mechanisms. We're going to present a lot of mechanisms in this class. In chapters 7 and 8, we're going to deal with SN1 and SN2, these two first order or second order overall reaction mechanisms. And then we're going to also introduce two other reactions that are called elimination reactions. There's going to be 4 of them total, and we're going to see how they, between substitution and elimination, and we're going to see how they compete with each other. And we'll learn some straightforward rules for predicting in any given situation what the outcome will be. The different mechanisms have different outcomes. That's not clear from what we talked about today, but it will be. Anyway, yes, that is the preview. So we'll just stop there because you need to go study for the test. Oh yes, question.
For the practice exam,
Yes.
how far are we supposed to be able to go?
For the practice exam, how far are you supposed to be able to go? I believe, I don't want to tell you something that's false. I think question 18 is maybe the farthest one. That's the one where you, I think, do some bond dissociation, enthalpy stuff. Beyond that, that's chapter 7 and 8.
Okay.
Yep.